so you don't have too much tonight. All right. Okay, so this is just going to be taking our power rule and using it for definite intervals. Okay, so whenever we have a problem like example 1, here is what we will do. And most of this is going to be calculator active. I don't really need that calculator anymore. So let's make this bigger here. All right, so we're going to integrate like we have been doing using the power rule. So for this problem, I would increase that exponent by 1. I'll get x to the third. I'll divide out front by that 4/3, or I'll divide by the 3, which will give me 4/3. And then I'll have a minus 2x, right? I'm going to put plus c right there, okay? Then, the 2 did not have an x with it, which means that was like an x to the 0 power. So you're raising that exponent 1 and dividing by the 1. So anytime you have a constant, it just gets an x slapped right there beside of it. All right, and we want to evaluate this from 0 to 3. All right, because we are integrating, and then we will evaluate from 0 to 3. All right, which means we need to do f of b minus f of a. So this is like our new function for our capital f of x, and we have to do f of 3 minus f of 0. So that will look like this. Our f of 3 part, we'll just plug in 3. So we'll have 4/3 times 3 cubed minus 2 times 3 plus c. And then we will subtract f of 0, or capital F of 0. So we'll have 4/3 times 0 cubed minus 2 times 0 plus c. Okay, so over here, one of this 3 right here will cancel with one of these 3's. So that'll be 3 squared, which is 9. 9 times 4 is going to give us 36 minus 6 plus c. And then over here, we just got c, because the rest of it's 0 and goes away. And so that's going to give us 30 plus c minus c, which gives us 30. So if we think about what this means, it's the area under the curve, which the curve is 4x squared minus 2, from x equals 0 to x equals 3. That should be 30 units there. All right. So all of that stuff that we did with Riemann sums and all the limits and stuff where we were trying to find the area underneath the curve, we can do this way as long as it's something we can use the power rule for, which is going to be obviously much, much easier for this. Now, I got a question for you. Is that plus c necessary? Why not? Yeah. Yeah, like no matter what I do, right? I've got a positive c here, and because I'm subtracting over here, I'll end up with a negative c. It'll happen every time, all right? You will always end up with a positive c and negative c, which will cancel each other out, right? So, I did this on the first problem just to emphasize that, but for definite intervals, and definite intervals are the ones that have numbers here. So it's like the integral from 0 to 3 of f of x dx, instead of just the integral with no numbers there, right? Definite intervals, the plus c is unnecessary. You can still do it if you want. It's correct to put it there, but it doesn't have to be there on definite intervals. Now, it's still really important if we see an interval where we're integrating and there are no numbers there, that we put the plus c on the end. Okay, questions? All right, in addition to the stuff that we have seen with the power rule, there are also trig integration rules, and you do have to have these memorized. These will not be given to you. I'll give you this stuff just because, like, it's going to be on the test so infrequently, and it would be so hard to memorize that I just don't think we'll have a lot of success with it. This stuff, integrate and trig, will be on there a lot. So you need to have it memorized for the test. But you should already have a lot of it memorized because you should know the differentiation rules, right? So the derivative of sine is cosine. So the integral of cosine is sine, right? If we take the derivative of cosine, it gives us negative sine. So if we integrate sine, it gives us negative sine. Okay? Yeah, sorry about that. Cosine. Negative cosine. So sines are backwards on the integration as they are on differentiation. If you are integrating negative cosine, it would be negative sine. Yes. We'll get to some problems in a second, William. I think you're confusing me. All right. So now, a lot of the trig, we don't have integrals for a lot of the trig because when we take the derivative of tangent, we get secant squared. So we don't have an integral for tangent. We have an integral for secant squared, which is tangent. Same thing for secant. The derivative of secant is secant tangent. So we can integrate secant tangent, and it goes back to secant, but we can't integrate just secant, or not just using regular trig rules. We can eventually do it, but we'll have to do something different. And then cotangent, cosecant, those are just going to be the same deal, but opposite signs for those. Okay, so let's look at some problems here. So I have to integrate sine x over cosine squared x dx. You cannot differentiate top and bottom of fractions separately, so that is not a route that we can go. I need to make this match one of the trig identities that I see, or trig derivatives and integrals that I see on the other problems. So when I have sine over cosine squared, that's not going to be sine nor cosine. We know that, right? I could break this up. No, we can't plug in yet because we have to integrate first before we can plug in the numbers. Well, we can turn part of it into tangent because sine over cosine of x is tangent, and then I could make this one over cosine x, right? Would you guys agree that this is the same? And then this is the integral from 0 to pi of tangent x. What's 1 over cosine? Secant x. Is that on your list? Pretty much. I think it might be secant tangent, but same thing, right? What is the integral of secant tangent? Secant. So when we integrate here, we don't want our integral sign anymore because we have integrated. We get secant x, and we are going to evaluate that from 0 to pi. So that means this is going to be secant of pi minus secant of 0. So let's think unit circle. Here it comes again. Right? Secant is 1 over what? 1 over cosine. So we're thinking like 1 over cosine. Pi minus 1 over cosine of 0. What is cosine of pi? -1. What is cosine of 0? Not 0. That would be sine of. This is 1, 0. X coordinate is your value there. So we're going to get negative 1 minus 1, which is negative 2. Okay. Questions so far? All right. Okay, let's look at logs here. If we take the derivative of natural log, we get 1 over x. So if we integrate 1 over x, we get natural log of the absolute value of x. Now, this is tricky because when you're trying to integrate 1 over x, it looks like you should just use negative exponents, right? But let me show you. You don't have to write this down. Let's think about example 3. Let's say I want to integrate 2 over x, right? I could pull that 2 out. Well, actually, let's not even try to pull the 2 out front. I could rewrite this as 2x to the negative 1. Correct? Then, if I try to use the power rule, what do I do to my exponent? I will add 1. It will give me 0. And then I will have to divide out front by that new exponent, which is 0, which is undefined, right? I can't do that. So this should be an alarm to you if you see something where you're trying to integrate and you end up having to divide by 0. That should have been a natural log, is what should have happened. So for the way we do need to do number 3 is we can just like pull that 2 out front and write this as 1 over x dx. What is the integral of 1 over x? Natural log. So we got 2 natural log of, it does have to have the absolute value bars there because you, whenever you take the natural log of something, it must be a positive number. You cannot have negatives there. And was this a definite integral? It was not. So we have to put a plus c on this one. We weren't plugging numbers into it, so we have to put the plus c. So let's look at this next example. This example looks complicated. It's got what looks almost like it should be a quotient rule sort of thing, but we don't know a quotient rule for this. What can I do so that I don't have to do like some sort of quotient rule thing? No, because this is not a limit as x approaches infinity. What? It can't come out of the integral. We can. We can make that x to the negative 2 times 3x squared plus 5x minus 2. And then we could distribute that negative exponent. So that would give me just 3, because the negative 2 and 2 would cancel each other out. Then I would have plus 5x to the negative 1 minus 2x to the negative 2. Or another option for that is you can do a love connection here, where you're dividing each one of those. It can be a triple love connection there. It's okay. Yeah, I mean, in real life I agree, but for math, triple love connections are okay. Upside down love connections are not. Yeah, no upside down love connections. That is not okay. But triple, quadruple, 5, there an infinite number of love connections are okay here, as long as they're not upside down. So, yeah. Or you, if the love connection makes you uncomfortable, you can do some negative exponents here, and that works also. You'll get the same thing. All right. So, whenever you integrate this, that 3 is just a 3x. What do we get for the 5x to the negative 1? If you try it, it's going to be undefined. When you have 5x to the negative 1, that is really 5 times 1 over x. What do we get when we integrate 1 over x? Natural log, which is crazy because it seems like you should not have a natural log in this problem. It's like it came out of nowhere, right? But it's there. Yeah, but that is natural log of the absolute value of x. Because if you try to use power rule on that, you're going to have x to the 0, and then you're trying to do 5 divided by 0. That's undefined. You can't do it. So there's a sneaky natural log that popped up in the middle of a problem that seems like it should have nothing to do with natural logs. And then the last one, though, we can use the power rule for that. That's going to be x to the negative 1 power. If we take negative 2 and divide it by negative 1, we will get a positive 2 right there, and we need to put a plus c on the end. They're easy, but they're sneaky. They're like you don't remember about them. There. Now, let's talk about an even easier one. Even easier is your e, because what is the derivative of e to the x? E to the x. So what's the integral of e to the x? E to the x. So when we take the integral of e to the x over 5, that's really just like 1/5 e to the x. That 5 is just a coefficient, really, right there. What are we going to get? E to the x over 5. And then we will need to evaluate that from negative 2 to 3, because this one is a definite integral. So we'll have e to the 3rd over 5 minus e to the negative 2 over 5. It just depends on what they give you for your answers. They might leave it like that. They might move that e squared back down to the bottom, and you'll have 1 over 5e squared. They might even get common denominators, which means you would have to multiply this by e squared on top and bottom, and you would end up with like e to the 5th minus 1 over 5e squared. When you get to stuff like this on your assignment, just check the back of the book to see how they left it and try to get it to match if it's odd. If it's even like any of these, this, or this, those would all be okay on a free response. There's no need to simplify, so I'd just stop at that first step. Okay, if we've got one like number 6, when we integrate 3 cosine x, what is the integral of cosine x? Sine x. So we'll get 3 sine x. And then what's the integral of 5e to the x? 5e to the x. They are for sure the easiest there. And then we would need to evaluate that from 0 to pi over 2. And so that would be 3 sine of pi over 2 minus 5e to the pi over 2 minus 3 sine of 0 minus 5e to the 0 here. Here comes the unit circle again. We thought maybe we wouldn't have to mess with it for a while, but all right, sine of pi over 3, pi over 2, what is it? 1. So we got 3 times 1. You can't really do anything with e to the pi over 2. Just leave it alone. And then we've got, what's sine of 0? It is 0, so we're just going to end up with 5 times e to the 0. What is e to the 0? It's 1. So we got like negative 5 right there. So we get 3 minus 5e to the pi over 2 plus 5. So 8 minus 5e to the pi over 2. I don't like it when I get answers that look like that. I like to have numbers, but there's just no way around it on these. All right, so your assignment that goes with this is, let's see, going to be page, I'll write it bigger up here, page 328. Let me see if I can give you all those. If I can cut back a little. Let's see, 328. It is a weekend. Let me see what we got. I mean, some of these are super duper easy, but 3 to 29. We'll do 11 to 21 odd. 27, 29. Let's do 37. 47 and 48. A lot of these should be pretty fast. So that is one reason that you have a few more than we normally do. They shouldn't be the problems that take you a long time. Next week, we are going to finish up Unit 6 next week. It'll probably be like early the next week that we have the test. The progress check is going to be our FRQ for next week because we'll need to do that progress check anyway. So that assignment that I gave you doesn't have like FRQ number 17 or anything. It says progress check number 6. So we're going to do that, and we're going to do it like our FRQ, and we'll have an FRQ quiz on Friday coming from that progress check instead of from one of the FRQ assignments for that. And then the next week, we will probably not have a FRQ quiz because we will have a test that week.